Hello, my name is Danish Lachmilis, and in this video, I will demonstrate LitmusKt, a tool for concurrency stress testing I have been working on with Evgeny Moisenko, Yaroslav Golubev, and Anton Podkopayev. First of all, let me introduce the problem we are addressing. Concurrent programming is weird and complicated. To illustrate this fact, consider the program on the right. It initializes some variables and then runs two threads in parallel. Each thread writes to one shared variable, then reads another shared variable, and stores it as the result. Now, the question is, which outcomes can this program produce? First, one thread can fully execute before another. So it will write one, then read zero, then that thread will read one, and we get one of the first two results. Then the threads can be executed truly in parallel. So each thread writes a one, then each reads a one, so we get the third outcome. And if you pause and think, it seems like that's all of them. Except if we actually run this program several times, we will eventually see this outcome. It may seem impossible at first, but in practice, the compiler can perform optimizations on our code, such as reordering independent instructions, and also the CPU can buffer some operations, and so on. Such behaviors that cannot be explained by a simple interleaving of program statements are called weak, and they are the main interest of our tool. As one can imagine, weak behaviors are quite tricky to reason about, and they pose a challenge not only to programmers who write concurrent programs, but also to developers of programming languages. For example, in order to correctly implement concurrency primitives, such as mutexes. Therefore, some form of testing is due. One way to test concurrency is litmus testing. It is somewhat similar to stress testing. First, we write small concurrent programs called litmus tests, and then we execute them repeatedly, trying to get all possible outcomes of the program. For example, the program shown in the previous slide is actually one of the standard litmus tests named store buffering. Litmus testing has been successfully used to find bugs in the real world. For example, there is JC which is a tool for litmus testing in Java maintained by Oracle, and it has found multiple bugs in multiple JVM implementations. There is also her tool suite, which performs litmus testing in assembly language, and it's widely cited in scientific papers on this topic. And as the company developing the Kotlin programming language, we became interested in doing litmus testing in Kotlin. One of the key Kotlin features is multi-platform, which means we want to do litmus testing not only on JVM, but also Kotlin native. And no existing tool could do it. So we decided to build our own tool, which we named LitmusKt. On the right, you can see the same store buffering test written in the syntax of LitmusKt. I will provide some details in a moment, but for now, let me list the key features of the tool itself. First, it uses the techniques from other state-of-the-art litmus testing tools like GC for improved efficiency. Then LitmusKt supports both JVM and native Kotlin, allowing to compare results from different platforms. And finally, LitmusKt comes with a set of classic litmus tests. And now I'm going to use this test in order to demonstrate LitmusKt in practice. Let me start by sharing a little bit more details on the store buffering test mentioned on the slides in the LitmusKt syntax. So first of all, we declare the state shared between the threads, in this case just two variables, and then we write the code for each of the threads quite straightforwardly. Finally, we declare which outcomes should be considered acceptable, interesting, or forbidden. Interesting means acceptable but also notable for some reason. And in this case, the 0,0 outcome is weak. So now if we actually run this test with our tool, we will see the following results. As you can see, the 0,0 outcome does happen in reality. In fact, it's even more frequent than 1,1 outcome. However, we can do even better. We can specify some parameters for our test. The optimal parameters are unique for each test, and we're not going to detail which parameters do what. But as you can see, using them can increase the frequency of weak behaviors quite dramatically. Now, let me move on to the next test I want to share with you today. It's called unsafe application. Here is how it is set up. We have a class with a single variable in it, and the state shared between the threads is a variable of this class. So one thread is going to write into it, and the other thread is going to read from it. What we expect to see is either the value integer value in this class, or -1 if this class was not initialized when this thread tried to read it. However, when we ran this test using Kotlin 1.9 with our tool, we actually saw the following results. As you can see, it was possible to read garbage values from an integer, which is completely unacceptable for a memory-safe language like Kotlin. So this was a compiler bug confirmed by the Kotlin native team. We actually fixed it, and it does not reproduce anymore with the current Kotlin version. So, to summarize the achievements of LitmusKt, it was able to discover a couple of new compiler bugs, some of which I just demonstrated. Also, we picked the interest of Kotlin native development team, and we integrated LitmusKt into Kotlin CI testing pipeline. That's all from me for now. Our project is hosted on GitHub. You can find it using this link. And thank you for your attention.